Okay, thanks everyone. So my name is Mahesan Niranjan, that's the way to pronounce it. So I have underlined Niranjan because that goes as my first name, informally Niranjan, formally Professor Niranjan, and of course my undergraduates go Professor Niranjan with a bow because they want high grades in their coursework. So this is a short talk of a piece of work done with three of my colleagues, Jiahui Liu, Keqiang Fan, and Xiaohao Chai. Okay, so there are students and colleagues in the room, and they would immediately predict that if I'm given a platform, whether it's 10 minutes or 1 hour, then I will start with this slide and go through this. And I'm going to try not to do this now, but this is a slide of everything you ever wanted to know about machine learning, which is everything you ever wanted to know about artificial intelligence. And this is about data, it's about fitting functions through data, it's about estimating parameters, making predictions on unseen data, carefully controlling what this model does so that you can guarantee something about what you can do on unseen data. It's about modeling uncertainty and huge amounts of things to do with probabilistic inference from which you can quantify the uncertainty of what you're trying to do. And that's about everything to do with machine learning, whether it is today or when this slide was written about 10 years ago or 30 years ago when I was started as a PhD student in machine learning. Yes, 30 years, I'm not as young as I look. What has changed is something Jeremy alluded to right at the beginning, is scale. So there are many problems in which we can solve many large problems, and that's driven by topics such as computer vision, topics such as natural language processing, particularly machine translation, proteins, chemistry here, game playing where you can generate loads of data. So that scale has changed massively since 10 years ago or 30 years ago. Okay? However, scale is not everything, always. You cannot talk about big data or big models without reference to what the underlying question is or what the problem you're trying to solve is. And when you try to do that, then things change quite a lot and quite dramatically. And that you might see an example of that in this talk. But when we moved to scale over the last 10 years or so with deep neural nets and so on, we came up with many tricks of the trade by which you can control how these models behave, how you can make them learn, how you can make them generalize to unseen data. All those tricks, quite a lot of them came as ad hoc searches in this space, tricks that people invented here and there, but we are also beginning to understand quite a lot of the reasoning behind those tricks and why they work and why some don't work and so on. So those are the recent developments of great interest. So driven by advances in computer vision, because we can do all sorts of things now and huge amount of money going into it with useless activity like self-driving cars. There's a huge amount of interest in medical imaging, and that's what this work is about. So medics make lots and lots of measurements, and there is a queue outside our offices to talk about applying advances that have happened in computer vision to making inferences from medical images, whether it's diagnostics, or prognostics, or more serious issues like only some patients respond to any type of treatment the medics have access to. And that's what's one of the crucial things that happens here. So let's calibrate. If you look at this scale here, towards the very right, or far right here, okay, that's only on my screen, is computer vision problems. We work with massive data sets of the order of 1 million parameters, million items of data, of number of classes going in their thousands and so on. So that's that point, that world. But this world will not necessarily produce magic to the more realistic world where we want to work in over here. There are some problems in medicine. We would work with 100, 200,000 data, things to do with chest x-rays, things to do with anything to do with optics and eyes. You probably can get huge amounts of data. And if you did that, your approach should be to train a models from scratch. Get a deep neural nets, and you train from scratch, you solve your problem with that. There are many interesting problems where the amount of data that you have is of that order, 1,000 to 10,000. And something that appears there very useful is the concept of transfer learning. And what is this idea here? You take a model that has been trained on natural images, on a large model that has been trained on large amounts of data, and adapts its weights or its parameters to this new domain that you have brought in with your 5,000 or 10,000 data. Why would that work? It would work because in the image space, you are not filling all parts of the image space. Natural images, medical images, they tend to live in a small part of that image space. So textures, shapes, curves, straight lines, these are the ones that fill that space. So there will be a small manifold in which any image that you give me would live. So some statistics or statistical relationships that I can glean from training models on large natural images, be they representations, be they parameters of the filters that pull out textures and lines and corners and so on, you could borrow them and solve problems here by adapting them to the new domain that we are interested in. Sometimes it's even rarer. There are problems where you only have 100 to 1,000 amount of data. And this is, again, partly because there are some, presumably there are some parts of the body you cannot image that well. There may be disease you are interested in that are not that prevalent. There may be the case that not every hospital would want to share the data that they have, so you're stuck in a problem with only about a few hundred images. Yeah? And that number is kind of crucial because in quite a lot of the large deep neural nets that we work with, the final representation that you have learned is of the order of these dimensions. What the neural net tends to do is to take your image, map it onto a space in which image classes become separable. And that space is typically in the region of comparable to this one. So we are now looking at a world where the number of data and the dimensions of interest in that final Euclidean space is comparable, or sometimes the amount of data you have is smaller, fewer than the dimensions. So that poses interesting problems to answer, and the idea of few-shot learning comes in that region. Okay, so that's the scale. And then there are, of course, some colleagues have approached me with 10 or 20 images and do some magic with it. The answer is go away. That's not particularly interesting. Very politely, of course. Okay, so one of the things we will see in what's coming now has to do with low-rank approximation, structured low-rank approximation. And you have already seen examples of this in the last two talks. So imagine you are given some data, and your data is number of data this way, and the number of features that you have derived from this data this way. So that could be, take your image, take it through some trained model, you are in the 512 dimensional final penultimate layer, and that's your features. So this type of matrix in which data is given to us often is of low rank. Why so? Some data can be very correlated, immediately reduces the rank. Some features may be correlated or derivable from the others, so this matrix will be low rank, and you can exploit that. How do we exploit that? If we factorize these features, now I'm in 1930s, around Fisher's time, yeah? Factorize this into matrices. I've drawn them to kind of scale that the number of features here is smaller, the number of columns here is smaller than the number of features, multiply by this matrix, so the product of these two matrices would be of the same size as this one, but this would be of low rank. The maximum rank is the width of this one, okay? So that's approximating a given matrix by a product of two things. Factor analysis is where this whole thing started. You can impose structure into this. And by structure, what I mean is prior knowledge about the problem domain that you want to bring in. If you insist that you want to approximate this matrix with this product, find k and x, but you want to have the columns of k and the rows of x as orthogonal vectors, then that's singular value decomposition is the term that gives you that. I've taken out the singular values in the middle, and that's exactly what principal component analysis is, as you saw in the last two talks. Yes? So you have approximated your data by a low-rank approximation, but insisting at the same time that your columns be orthogonal. Okay? Sometimes data is all positive, and we can do some more tricks with this. What can you do? You can factorize this while insisting that both k and x be positive elements, only contain positive elements. Once you force that, that's called non-negative matrix factorization. Yeah? I'll come to that in a second again. So SVD, or principal component analysis, as you in the last two talks, the job of it is to preserve the variance in this data. So you give me this data, I want to approximate this, but the variance that I find in this original data, what's the best way to preserve this? This is what SVD is going to do to us. It immediately follows that if you thought your data is multimodal, maybe coming from 2 different experiments, maybe coming from 2 different labs, maybe coming from 2 different classes of images, then this is not perhaps a good idea to do. Yeah, that immediately follows from that. Something special about NMF is because I'm trying to force all these elements to be positive, the solution to approximating this will throw in loads of zeros. Yeah, if something has to be negative to make this approximation good, I'm forcing it to be positive, non-negative, therefore it will end up being 0. So what that means is that this factorization gives us a sparse representation, and an interpretation of that sparsity is that it gives me a parts-based representation of reconstructing Y from the product of these. Like I just said before, what is of interest is the regime where the number of data and the number of features are comparable, or the number of data is actually smaller than the number of features that's of interest. Okay? And we'll come to that in a second, and that's the kind of range in which we are operating here. Okay, so what we do is this. Go into medical images. So these are medical images of various types, cancer versus non-cancer, or a particular type of disease and another type of disease, or different types of disease, all labeled from imaging data. We run it through a deep neural net that has been trained somewhere, and these are very easy nowadays to get. You don't have to train them, you can just download them. They have been trained, you know the architecture, you know which data set it has been trained on. You also know all the meta information as to what the training regime, etc. were. Okay? And that maps the image, any image given to me, in a 512-dimensional Euclidean space. That is how they are distributed. So once that's distributed like this, and you suspect that the number of images is smaller or of the same order as 512, you think it is not a good idea to do pattern recognition in this space, because you have fewer data than the dimensions you have. So that's immediately leads to ill-posed problems. You don't like it, so you need to regularize it somehow. And the immediate temptation then is to reduce the dimensions. You give me some data, I want to reduce the dimensions. And the typical thing that's most popular is to reduce by principal component analysis, which is the same as SVD, singular value decomposition, reduces to this. And like I just said, that is perhaps not a good idea if your data is multimodal, and if your problem is classification right from the beginning, then your data is necessarily multimodal in this space. Yeah? And if it is multimodal, then PCA is not a good idea. So what we were exploring in this work is, are there alternate ways of doing this? Are there alternate ways of looking for lower dimensions which could help better? One is NMF, non-negative matrix factorization, because over here it's all positive data, because these days we work with this ReLU nonlinearity all over the place. So data is already positive. Can we have sparse representations as lower dimensional subspace? The other is, can we go into discriminant analysis? Because as soon as you know that things are multimodal, then it tells you why not look for discrimination in that space, because for the problem we are trying to solve, we also have class labels here. So why not use them while reducing the dimensions? So that's discriminant analysis. So that's what we have been doing in this piece of work. So just to go through what's going on here, that's singular value decomposition. All of you know this. This is in the first lecture of Foundations of Machine Learning we teach. So you take a data matrix, you factorize it into orthogonal matrices and the singular values that carry the weights of them. Going back to Fisher, there is linear discriminant analysis. And the idea in linear discriminant analysis is to say, can I find a subspace in which the different classes separate as much as possible in their means, but any class, data from any class, is tightly scattered within itself. Yeah? So within class scatter should be small, between class scatter should be large. And that criterion, that's third lecture of Foundations of Machine Learning, has an objective function, which tells you the numerator, which is how far the classes are scattered, should be large, very large. And at the same time, the denominator, which is how each class is tightly scattered, should be small. So you want to maximize this ratio. And that reduces, in a multi-class case, to a generalized eigenvalue problem. And if you solve this, if you had C classes, you can immediately find by solving this a C-1 dimensional subspace. Yeah. The between class measurement is not full rank. So if you have C classes in some P dimensions, even though the matrix is P by P, its maximum rank is C. So you can only pull out C-1 dimensional subspace out of this, but that's still a very, very useful subspace. So that's all in current machine learning course I teach. So when I had PhD students come along and say, I want to do something interesting, say, okay, that's in your coursework, so go ahead and do this on medical images, right? Something else we pulled out from a very long time ago with Foley and Salmon. This is in 1975. This is before I went to university, yes, very long time ago. And these guys worked out a really cool thing to compute discriminant directions recursively. So you are in a multidimensional space, you look for the first discriminant direction. Which way should I look so that the data is maximally separated? Then you hold that constant, and okay, so that we all know how to do. We do that, there is a discriminant direction immediately pops out. That's Fisher's linear discriminant. You can now ask the question, can I hold that constant and look for a second direction in that space which maximizes that same ratio, but orthogonal to the previous one? Yeah? And if you did that, then the same measure of the ratio, there is a second direction, and I throw in a Lagrange multiplier, and I say the scalar product of this should be 0. Yeah? So orthogonal to the first one I have computed, can I compute a second one such as this ratio is maximized? And the solution to that is in the 1975 paper. Those days, LaTeX was very expensive, printing was very expensive, so they didn't give us the whole derivation. They just gave the results in the paper. So when Jiahui came along as a PhD student, I said to her, just go and derive this and convince me that this is correct. Her first reaction was, yeah, okay, all the dimensions add up, therefore it must be true. And then she spent a lot of time and actually derived it, so this is now true. Okay. You can build on it. You have D1, you have D2, you can hold those two constant and look for the third one and keep going. What you can do is you can find the nth direction as a function of the n-1 directions you have computed so far by solving, multiplying these matrices. So there's a recursive solution to finding subspaces of increasing dimensions on which your data is maximally separable. Okay, so that's already looking good because we started by saying if we were to do PCA, we are thinking all the data is in one place, but that's not the case. It's multimodal, so we are respecting that in doing this. NMF is almost textbook stuff now. You have a data matrix. You want to approximate it by a product such that all the elements of them are positive. And there are many variants of a multiplicative algorithm to do this. You first update the k, holding the x constant, then you hold the k constant and update the x, and you keep iterating around this. Each of these updates would be solving a convex problem. Together they are not convex, but still you can get to decent solutions out of it. There are many variants of this. You can impose all sorts of things on this. You can say, okay, this produces a sparse factorization, but if I want it even more sparse, can I impose additional sparsity constraints on this? This is possible. You could say you could force the sums of rows of k to add up to 1 and pull out and force this to solve a clustering problem. There's a whole bunch of variations to this. So those are the two things we are looking at. We take your medical image data, throw it down to a 512 dimensional space. We have about 200 training data and about 150 or so test data. What's the best classification we can do? A, in that space. B, that space reduced to a sparse axis-aligned space by NMF. C, that space reduced to a discriminant analysis-based subspace. That's the story. Okay? Now, if you were to do that, okay, sorry, I forgot this one. Whenever you talk about NMF, you have to show everyone this picture. This is a landmark, a classic paper on the subject. The topic has been around for some time, but when Li and Seung figured this out and wrote this paper in Nature, it caught the attention of many of us. The idea is that you want to construct this phase. PCA or SVD will variance preserving. So the very first one already has almost that phase. Yeah? And then add to that combinations of second, third, fourth, and so on, you reconstruct this face accurately. With NMF, it's parts-based. Because lots of these are 0, you are reconstructing this as a weighted combination of these guys, and you can go and try and interpret it. If you're lucky, if you look here, you see a little bit of eyebrows here. If you look here, you see a bit of a mouth here. Yeah? So the reconstruction is based on little parts as opposed to a variance-preserving principal component. That's the basic idea. Vector quantization is just take all your data and cluster it. Then this one becomes the nearest neighbor is to reconstruct this one. Okay. So when we do this, how am I on time?
A few minutes.
Okay.
9 minutes.
Okay.
9 minutes, very precise.
So when we go and do this, what do we get? So you're going to see a lot of numbers and graphs, all of them to convince reviewer of the journal to which this has just been submitted this morning that everything I say is actually true. So here is a comparison on a 2-class problem, I believe. At various different dimensions, if you had chucked the data by PCA, if you look for the very first direction, the first principal component, then the data has all been on top of each other. So there's actually no discrimination there. Yeah, whereas the Fisher's discriminant pulls you out something like 0.69 or so. And as you sequentially add that Foley and Simon's work, look for higher and higher directions, then the discriminability of both of them go up. But a subspace that respects the fact that the data is actually multimodal would perform significantly better than one that lumps the whole thing by principal component analysis. And of course, if we did one, then nobody would be happy. So we did this on 14 different problems, spanning about 11 different disease types and 3 or 4 different measurement modalities. And across the board, and there are, I can't see that here, on the right-hand column, you see the number of classes. Some of them are binary problems, some of them are 8 class, 11 class, and so on. These are benchmark data sets that are publicly available. So they actually have more data than what we are using for this purpose. So we subsample that to make the point. Okay. And across the board, except in one case, it turns out that there is good value in doing 2 things. The first is in reducing the dimensions. It makes sense to reduce dimensions. The second one is makes sense to reduce dimensions, respecting the fact that the data is multimodal, so that the discriminant subspace gives you a better representation to do your classification than your original subspace. We were doing k-nearest neighbor classifier, so the right thing to do is to see if that has an effect. So k equals 1, k equals 5, k equals 10. It gets a bit boring to do these things, but well, PhD students have to do this, right? So they have a degree dangling in front of them. So across the board, if you did discriminant analysis, that makes a lot of sense to do. We looked at what happens if you had tiny amount of data, and is there an effect if you had a little bit more data? And of course, when you have more data, performance is better, but the relative thing of the advantage of doing discriminant subspace as opposed to principal component analysis is very clearly borne out. I'll come back to this one a little bit later. NMF does similar, and the most interesting thing about NMF is that it gives me an alternate way of reducing the dimensions as opposed to singular value decomposition or PCA, which is very well known and well tried. We're a little bit suspicious whether that would be the case, partly because NMF produces a sparse representation, so you might be losing stuff, partly because NMF is a non-convex problem when you actually estimate the factorization as opposed to SVD. What that means is every time you run the algorithm, you will get a slightly different answer. Yeah, so what would the effect of that be? And that's fairly robust to that. And that's what runs through binary problems, multi-class problems, and so on. Maybe I should jump a bit far. So this graph, for example, shows you that as you increase the dimensions, the reconstruction error monotonically goes down. You do bigger and bigger subspaces. You can construct the original data better and better. Yeah? But in terms of how you can do discrimination in that lower space, the sudden jump comes very early on, and then very quickly that kind of saturates. Yeah? And again, we ran a comparison between NMF is NMF a viable alternative to SVD on all the 14 problems, and there are small differences. Those differences are not that significant in this context, but very quickly you reach a plateau where both are comparable. Something else that became intriguing was, okay, so we downloaded this ResNet pre-trained on the ImageNet dataset and used that as the feature extractor. What would have been the case if we just randomly initialize that network and have a transformation? Yeah? So your network has not learned anything from outer world out there, but it's just a bunch of random numbers of a particular architecture. And all it does is take the medical image and map it into a 512-dimensional space. And that is not that bad either. That also produces decent results. If you look horizontally here, the pre-trained image-based, image-trained one produces certainly better results on average than if you randomly initialize the model. Yeah? But when you randomly initialize it, still, it is a fixed transformation of all your data. That being the case, there is residual discrimination in that, which you can pull out. Okay, so to conclude, I'm going to make some very obvious observations, and I have certainly proved that obvious things are true. Dimensionality reduction helps, and I think nobody can challenge that. Principal component analysis, or SVD, in multimodal data is perhaps not a good idea. NMF can be a decent alternative, and there are things about NMF we have not exploited. I'll tell you in a second. Discriminant analysis, because the data has class labels and a bunch of classes, discriminant analysis offers you a much more effective subspace to reduce the data before doing further classification. What are unfinished businesses here? I think Jiahui and Keqiang have 2 more years to go. One is we are not exploiting the fact that in the NMF we get a sparse representation. If it is a sparse representation, then we should be able to build compact models out of it. We should be able to say you only retain parts of that space, so when you do further computing, you should be able to do this much faster, store simpler models, and so on. The other is, if it is parts-based, there must be some possibility of deriving some explanations out of it, which we have not really thought through as to how to do. If you recall Lian Xung's face picture, it was pulling out faces as a combination of different parts of the face. So there is some explainability out of that as to what is dominant in making a decision. We haven't really thought that through. The other, of course, is the queue of clinical people who want to work on it at the university hospital down the road. And downloaded data on which we normally spend our lives has its limitations, because we download image data and we build an algorithm, we quote performances in terms of tables and graphs, and we stop there. But working with clinicians, we have clinical information. If you had clinical information, there are a couple of things you could do. One is integrate that clinical information down here, because we collapse the model into the image into 512 dimensions, reduce it to 20, 30 dimensions, then adding 5 or 6 clinical variables in that space makes an enormous amount of sense. I can't integrate the clinical variables out here in the image space. The other, of course, is interpret classification errors. We don't want to stop with accuracies. You want to know what errors the models make. Is there a way of working back and interpreting, explaining them, again, in the context of clinical variables? Yeah, sorry, I might have overrun a bit. You could always hit me.
All good.
Okay, thank you very much. Let's pause here. Yeah.